So I'm going to talk about our recent work in robotics and autonomy and AI specifically for robotics, right? And I've been to the Middle East. I think about 3 years ago, before the pandemic, we were in Abu Dhabi, and I'm just always tremendously inspired by the types of amazing things that are being accomplished in that area with all the scarcity of water. And I really think that one of the things that we've been trying to do with our robotics work is that, we like to tell ourselves that we're trying to make the robots that'll go to Mars when Elon Musk makes his rockets to get us there, right? And that's kind of my route back to the aerospace. As Eric had once said, Girish is well grounded nowadays. But we definitely have to start on our Earth. I think there's a lot of healing to be done. There's the deserts, but just even if you just look at the US Midwest, there's just a lot of things that are happening that should be reversed if we are to take care of our planet. So towards that, the question is, what can robotics do, right? And so that's what my group does. We work on field robotics, we work on learning, we work on autonomy, like I'm sure many of our colleagues who do the same things. But the key question is, how can we bring together these technologies to try and have some kind of a positive impact on the climate? And just as a brief introduction to my group, whose work you're going to see, we are a number of students from a number of different disciplines across campus at UIUC, and like just really very diverse, and there isn't like one specific department that isn't well represented. And what we kind of work on is this, what I like to call full stack autonomy, right? Or full stack robotics. So the hardware and the software. And the software typically has these three big kind of modules that people worry about: perception, planning, and control. And there's a lot of good, deep work in all of these modules, in our work and as well as other people's work. But the big gap that still remains between where we are today and where we like to be in robotics is this issue that just happened in this on this airplane. This was actually work that I did back at Georgia Tech. And what happens is, during mid-flight, the airplane loses half of its wing in mid-flight, and we purposefully make it do that. So purposefully we throw half the wing off. And the real question in field robotics is that when things like this happen, now this is a very dramatic change, like not necessarily even to this magnitude, but when things happen that are uncertain, that are unknown priorly, what does the robot do? And if you see where robotics has been successful today, like in structured environments, there's a lot of control over what things can happen. And as a result, the level of uncertainty is very low. But when you're out there operating in the field in harsh environments like in this airplane is, or when you're in the fields or in the desert, there's a lot of things that can happen that you don't really know before. So the question is, how do we create autonomy technologies that are able to adapt? So this is kind of the work that we've been doing for a long time. But about 2016, we started pivoting a lot of this work towards agriculture. And we had this foundational belief that robotics and AI will make farming sustainable and profitable. And a lot of things have happened around that at UIUC. One of those is the Center for Digital Ag, which I'll talk a little bit about. The other one is the autonomous farm. And the third thing is the company Earthsense that I've co-founded and incubated at UIUC. So the reason we did this shift is because a lot of us know that we're really, agriculture is out of balance, right? And food is like the primary kind of basis of human civilization. So agriculture is the original technology, right? Original engineering. Even before the wheel, we were figuring out how to try and farm. And it's not that we cannot make enough food, right? We cannot distribute it properly right now. But the worst part of all of trying to make enough food for our population today and the growing population by 2050 is that the environmental impacts are just tremendous. So what would be nice to do is bring this into balance, right? So that we can create more food to support a growing population and clothes and fiber and fuel, but at the same time help the environment. So right now what has happened is that the environmental incentives are not really in line with the farmers' incentives of creating profitable farms, right? And nowhere in the world is this in worse shape than in the corn and soybean agriculture, right? It is like these large scale, humongous monocultures with very little profit every acre just drive a tremendous amount of effort. Like, you have to put a lot of chemicals in to just make this prairie land be in the stable equilibrium of a monoculture, which it shouldn't be. Like, if you just let it be, it will be in a prairie equilibrium. So the question is, how can we help farmers bring those incentives back into balance, right? And we believe that one way of doing that would be to create robotics and AI technologies that enable some new options for farmers that are foundationally more sustainable than the options that they have today, which is large-scale chemical spraying. So some of these examples are, for example, under canopy phenotyping. So we really believe that if we can make little robots, and little is relative to the task they have to do, but if we can make teams of robots that can be that can get really close up to plants, like in this case they're under the plant canopy, then we can accomplish a number of new things, such as under canopy phenotyping, mechanical weeding, reducing the amount of nitrogen that's sprayed, adding cover crops, and then also enable polycultures over time. And I actually also think that this technology, and I'll try to talk about it a little bit since we have an audience from the Middle East, like how some of these technologies could actually be applicable in areas that are very arid, such as in the Middle East. So of course, this is like a dream, a vision that's more than a generation's work. So obviously not something that, all of it is not something that we're doing right now, but we're building a path towards how to get there. And we feel that the foundation of all of this is really better seeds, right? And we'll talk, so I'll primarily talk about that a little bit in my talk. And then the next is reducing the amount of chemicals that we use. And then what I'd like to do in the next 10 years is try to build more towards productive ecosystems and integrative ag, which combines animals and normal crops. So let me start talking about the seeds. So you may know or you may not know, but corn, which is like a very common plant now in the Midwest and all over the world, is actually not a natural plant. And it's really appropriate to think about the contributions made by Native American and Mesoamerican populations to agriculture during this week of Thanksgiving, right? So corn, for example, comes from selectively bred from this plant called teosinte, in which I think somewhere in South America, folks bred together over a period of 9,000 years until the modern varieties of corn start appearing 3,000 years back. And this is not just the case for corn, right? Many other crops that we consume today have been selectively bred. A number of them have happened actually in the Amazonian food forests, which we'll talk about a little bit later. So, of course, but it took quite a bit of time. The question is, how do we create the next generation of seeds in environments that are that haven't seen this level of agricultural breeding programs, right? For example, in Africa or in India, where the populations are going to be doubling, but the yields are a third of where they are today. So in order to do this, plant scientists work on techniques called genome-wide association, right? So in this technique, what you have is that you have all the genes of the plants that you care about, they're all sequenced. And what you're trying to do is find the genes or the genotypes that are responsible for the phenotypes or the exhibited traits of the plant with respect to the environment that the plant is in. So this could be just the weather, but it could also be the soil type or the chemicals that you're adding, the management practices that you're doing. And if you can do this, then you have a more directed, more specific approach to plant breeding that doesn't hopefully take 3,000 years, right, to get the next version of the plants that we need. Now, the unfortunate thing is that there isn't really a simulation model of a plant. So what breeders have to do, and these include university breeders as well as large companies, about a $10 billion a year industry, in just coming up with these different types of seeds and products. What they have to do is they have to run what's called a diversity panel. So this is one example of it. This is about 40 acres. And in those 40 acres, they have planted about 800 varieties of sorghum. And though these are slightly different than each other, and they're seeing how these varieties are going to perform in this particular climate. Now, overall in the world, I think there may be about 10 million such trials. So each of this plot or experimental unit is 3 by 3 meters. So about 10 million such experimental units every year are tried out around the world. And the big problem is that a lot of this measurement of these plants is done entirely manually. Like this person is counting, these two are measuring the stem height, this one is measuring the stem width. And the issue with that is that it's extremely labor intensive, but it's also not very accurate. And it's very difficult to scale up. So the big question in agriculture has been, how do you scale this up? And they call this the phenotyping bottleneck. And the question is, how do you, like the big kind of the hypothesis is that if we can alleviate this phenotyping bottleneck, then we will be able to create better seeds, which are foundationally more, like more water efficient or more nutrient efficient and more higher yielding, so that, agriculture can improve from the bottom up. So how do you do that? You can do it with these gantry systems, which have limited area and are expensive to maintain, but they can get you a lot of data. You can do it with drones, which really are low cost. They can cover a lot of areas, but they don't really get you the data from under the plant canopy. Or you can do it with robots. And robots is where a lot of people have been focusing their attention on, and not just for this, but there are many other applications of robots in agriculture. But if you look at where robots are today, right, there's a lot of concepts and systems, prototypes that are out there, but there are very few actually deployed robotic systems in agriculture. And if you ask what is going on, then you find that it's really the cost that matters, right? So one part of the cost is the cost of the robot itself. And in all honesty, at scale, I don't see why electric robots should cost more than tractors to make. In fact, they should cost less because we don't have an engine, a diesel engine. But so the real cost is not the cost of making the robot, it's actually the cost of autonomy. Like, for example, this robot, you can, at that point in time, it was made for 25,000 euros, but that doesn't, and it was shown that even at that price, it was equivalent to like one person doing some tasks in the field. But what that cost didn't include is the 5 people babysitting the robot, right? And that's where really the big challenge is in getting these robots to be autonomous, which is a difficult problem because these fields are just huge. The data that you get in those fields is not very good, and the environment is fairly unstructured. So this was the problem that we started working on in 2017, 2016, 2017. 2018 is when we published our first paper of this idea of making really lightweight, low-cost robots that are also autonomous under the plant canopy. And then they can do the first most useful thing, which is high throughput phenotyping. And this appeared in our RSS 2018 paper, which got the Best Systems paper award. So let me try to talk about the whole robot concept first. So mobile robots, of course, have been around for a long time. I think the big question for us, and before we came to agriculture, a number of people are focusing on these much larger form factor robots, right? So this is an example of the smaller ones of the much larger form factor. And you'll see that it kind of just kills this plant there because of the tracks it has. So one of the things that we tried to do when we got in here is we leveraged our aerospace kind of thinking, and we started thinking about, well, what's the smallest robot? What's the simplest, lightest robot that can actually do this job? It doesn't have to be over-engineered like this robot is. And the answer was basically a drone on the ground, right? So initially we really thought seriously about whether we can fly drones through the fields. And I think in certain canopies it's possible, like in viticulture and other ones, but in corn, there's just not enough space for a drone to fly in there and not have to deal with a lot more problems than a rolling robot would have to deal with. So we came up with this idea, well, what if we just make a little robot? And I think one of the biggest questions in everybody's mind at that point was, well, will this little robot survive the field conditions, right? So what we did in 2018, and this is, we had this project called ARPA-E TerraMap project, and Earthsense became a commercial partner for this project. And we started making these robots. We made a 30 of these 3D printed robots, and then we gave them to a number of people in the industry, like companies as well as researchers, to basically figure out whether or not these robots were useful for them. And they put them out in the field, and they broke all the time, of course, because this is the first time we made these robots. But we learned a lot of things about the data, and particularly people found that that data was useful, that RSS paper was published, and a number of people were just very excited about the compact form factor of this robot. They were like, yeah, I can just pick it up, put it in my truck or car, drive down to the field, get my data recording done, and move on to the next field. So in 2019, we revisited the design. We completely changed how the robot was made. It was now vacuum formed plastic, a Monoc chassis, which basically is very rigid and tough, you'll see. And the shafts and the axles were all now made with metal. And the motors were converted from geared brushed motors to brushless DC motors. And every year we've been kind of improving it. This is our 2020 version. And it primarily looks very similar to the 2021, except for one big difference that I'll talk about right after. But it has one LiDAR sensor here, one LiDAR sensor here. These are 2D LiDAR sensors, so Hokuyu 1500 GLX or something. And then these are the camera sensors 1, 2, and 3, and upward facing camera here, and an integrated RTK GPS receiver. And then inside the robot, we have an i7 computer with lots of compute power, and another Raspberry Pi computer that's actually running the motors. And all of this is on a custom-made PCB. So one of the things that people always wonder or worry about is these little things. Is it going to survive field conditions? So one of the things that we've really found, and I think this is a very important lesson that I think all of us learned in the aerospace industry, is when most of us were focused on trying to miniaturize helicopters, the drones that actually became successful look nothing like any other aerospace vehicle that's out there, right? The four quadrotors, right? And I think what didn't make a lot of sense to those of us who were thinking in the traditional sense is that even though that design for an aerospace vehicle is maybe not the perfect design for carrying people, it makes a lot of sense at that size. And I think that's kind of what we found here with the little robots too, is that when you go really small, you don't have to have all of the systems. You can really simplify the robot and still make it extremely strong for the size. So the only moving components here are these 4 wheels, right? This is a skid to steer robot. It doesn't even need tracks because the weight is not that heavy. And as long as we can make those wheels have low pressure on the ground, this thing is able to basically drive through most agricultural environments without getting stuck. There are, of course, always going to be limits to what any wheeled platform is able to accomplish. But since this is really not designed to, for example, go in very heavy grass area, it might get stuck in places like that. But that's okay, because you can always just extend the height of the wheel, the ground clearance, and things like this will work out. But the point is that like any other design, there is a trade-off to be made, and the compact form factor and the ease of use, like for example, here in India, people are just carrying it on the back of motorcycles, right? Is really a powerful way of designing rapid use robotic platforms that actually get useful things done, such as plant scouting, and B, help us accelerate autonomy research. I also want to show this video. This is a 2021 robot. Now, we've made a lot of improvements, primarily inside and to the motor systems. These are now much higher torque brushless DC motors. And I just want to show this video because a lot of the times people really underestimate the power of small, right? Like how much torque these little 4 motors can carry. Now, each of these motors is what you would have on a little scooter, right? So this is the robot that's our engineer sitting on it, and it's pulling like a small John Deere tractor, which is, you know, quite heavy beast with a lot of static friction. So these things can really pack a punch. And that's really not just, you know, of course, not just our robots, but other robots also could be designed in this particular way. Now, the next question is, once you have these robots, is how do we make them autonomous, right? So everybody starts with GPS, which is the state of the art in agricultural autonomy, right? And it works great when you have access to the sky. And I won't get into the details of this, but we've published a number of papers that basically try to get GPS-based autonomy working really well by specifically estimating the slip coefficients, because this is a skid to steer system, and you cannot assume that it doesn't slip because it slips all the time, and unlike a differential drive. And primarily my postdoc, Erkan Kaichan, who's now a professor at QUT, or University of Queensland, and he's now coming to University of Georgia University of Oklahoma, has published a number of papers in this area in which you've devised this nonlinear model predictive control and non-linear moving horizon estimator to estimate the states of the robot with GPS as well as the slip coefficients. And you know, these types of things work really well when you have access to GPS. But the issue is that when you're under the plant canopy, GPS starts being very unreliable. So here the robot's driving under, and you see the GPS distance estimates. They are about 40 centimeters. There's this noise of about 40 centimeters, right? Whereas outside of the canopy, this should be less than like 2 centimeters, really, if you have real-time kinematic GPS. So this type of error, 40 centimeters of error, is not good enough when you want to navigate a 100 centimeter canopy. Not only that, right? What you really need is this reactive navigation. So you have to find these rows, and then you have to navigate with respect to the rows, because the plant, like if you prescribe the waypoints from before, the field may be different. There may be different things. The plants might have grown differently. So you will not be able to adapt to the in-field conditions. So the foundational robotic row following problem is something that we have been working on. In 2018 JFR paper is where we kind of introduced this problem, and in its current form. And the idea is that this robot needs to figure out where the rows are, so the distance from the row and the angle to the row, right? It's like the simplest perception problem that you can have in agriculture. And the issue is that the data is extremely noisy. So for example, this is where the LiDAR is, and the robot is moving forward in the canopy. And this is the point cloud that the LiDAR is getting. So remember, the LiDAR is just getting range measurements from its spinning laser. And you can see that it's really difficult to identify lines in here, which is what our algorithm has to do. And this is our algorithm in action. And this is explained in this JFR 2019 paper, which I'd welcome you to read in detail. But it uses basically a fastened up version of RANSAC, if you want to look at it that way. Or in another way, it uses heuristics to speed up the estimation of these rows. So these types of heuristic-based systems have been something that we've been testing quite a bit. And we're quite proud of actually not just publishing good papers in this area, but actually trying to deploy these out there in the field, right? And not, I mean, it's great to basically have the robots drive for 500 meters, that's maybe enough nowadays for papers. But what we really need for impact in the real world is that these robots have to operate for miles and miles and hours without any issues, right? So we always adversarially test our robots. Like this one's trying to go down the row, but we're like making sure it has a hard time doing it. And that's good, because as a result, this technology now is seeing its first kind of impact into the real world. So last year, Earthsense made 100 of these TerraSentia robots, and they deployed them for high throughput phenotyping. And I'm not going to get into the AI that they are working on, but things like width estimation, finding the ears of corn, estimating their height, then finding counting the plants themselves, right? So there's a lot of detection and tracking machine learning algorithms that they work on, and then finding the height of the plants. And the key thing that they do is they don't do it just on one plot or 10 plots. They do it on 100,000 plots of data, right? So there's data that comes in, it needs to be allocated back to which experimental unit or plot that data comes from, and then the results need to be processed, and this needs to be provided back to the user. But the good thing is that all of this is now kind of working, and so we're seeing kind of the first exciting introduction of robotic technologies into agriculture at some kind of a reasonable scale, other than drones, of course, of ground robots. So the question is, how do we take it from these R&D fields now, more or less, into the fields of the farmers? So for that, we need to kind of look at where farming is today in the profitable countries, like in the Midwest, right? So farming today is only profitable at scale. So you have to have a large farm that generates, especially in this commodity row crop farming like corn and soybean, you have a large farm. So if you have a large farm, you need a lot of labor to kind of deal with it, which is very expensive. So what farmers do instead is they use the available tools, which essentially rely on using chemicals to replace labor, right? So for example, for weeding, for pesticides. Now, this in itself has several issues. So we know about the nitrogen that's just like leaching into the oceans, the pesticides that are in our food, but there's also issues like the herbicide-resistant weed crisis. So the spraying of herbicide on varieties that are resistant to the herbicides, like Roundup-resistant corn, has actually proliferated the emergence of weeds that are also resistant to the herbicides. And things like this can cost a lot of money, and money is not even the point, because not entirely the point, because it really affects also the environment. And if you go to India and Africa and other places where people are doing subsistence farming and the farms are much smaller, they're still having to rely on labor. And this labor is not really working in very good conditions, very difficult to find. And one wonders why. Well, not really, because the farmers are not able to pay the labor enough to actually be able to consume, commensurate with the kind of work that they have to do in the farms. They can get much higher paying jobs by going into the cities and working for construction or as maids, for example. And if you look at all over the world overall, right, farming, the amount of money that farmers keep has been reducing, primarily because commodity pricing on top and the amount of chemicals that the farmers have to use in order to keep up with the kind of supply that they need to produce to be competitive as a farmer. And this is in the US, for example. The cost of labor has been consistently going down, right? And so the amount of labor that's been used in the farms is lower and lower every day. So in the 50s or 60s, I think it was like about 62% of the US was in agriculture. It's like less than 2% now. The cost of land is going down, which is kind of indicative that more and more marginal land is being used for agriculture. But the way that's happening is because the intermediate goods or the chemicals the cost of that is just rising. So the amount that's been used is just increasing to a point where it's actually exceeded now the cost of capital, such as tractors and other things that are required. So this is a very interesting and in some ways worrisome trend. The good thing about it is that this is the green revolution, right? We are able to have food and we're able to do these talks and work on computers and things because the food problem has been solved because of the green revolution. But it's kind of the issue is that if we continue to do these same things for the next 20, 30, 40 years, we're going to be in trouble. And ideally, we would like to be in this Amazonian food forest, extremely diverse, self-supporting, multi-layered agricultural, polyculture, permaculture environment. And that's major goal for what we're trying to do. But in the meantime, like between here, like automating the tractors, which I think the large companies are already doing, which will just accelerate large-scale monocultures, and polycultures, which is what a lot of roboticists want to do. I think there is something in the middle, which is like just improve diversity of cropping in these large areas by just adding more options for farmers. So let me give you one example of this. So for example, right now in the US Midwest, right? So it's like, I think 200 million acres of land that in the late fall, winter, and early spring months is just left bare, right? So people will, because it's the winter, so once they harvest their crops, now this land is just sitting bare like this, which is not good for the land. It's not really doing anything. It's not regenerating. Just a great opportunity for weeds to grow up, and is not really, sequestering carbon. If you look at corn agriculture, it actually, and overall agriculture, it puts 10% of the global greenhouse emissions, which is ridiculous because agriculture should really be sucking carbon rather than putting it in there. Now, there is one way of fixing this is to grow cover crop, right? So the cover crop is just basically a ground cover, right? So you plant it, it takes hold, you harvest the corn after, and it's just there throughout the winter. Some of it dies, some of it might stay up, some of it comes back up when you're into the spring, but it's basically not letting the soil be bare, and it's pushing carbon in. It's making a lot of humus so that biological activity in the soil continues. But most farmers are not able to do this today, because if they do it using the tractors, they have to do it post-harvest, which is too late in the northern latitudes. If they do it during the season, they have to do it using airplanes, which are quite expensive. And as an aerospace engineer, I'm keenly aware of the amount of fuel that they have to spend to put that amount of corn out there, which is kind of, I'm not sure if the net carbon gain is positive or not. Sorry, not corn, the cover crop out there. Or they have to use large sprayers like Hagee sprayers, which end up hurting the plants a little bit. So the question is, how can we enable this at a lower cost, right? So one of the things that we've been thinking about is if we take the same technology that we have and make these under canopy planting robots, then we can basically plant cover crops. And it seems like we should be able to do that at much, much, much lower cost than is possible with tractors. And I see a question here about why motors don't. So let's get back to that question when we're done with most of the talk, about how I feel electric things should actually cost less than tractors. But if we can get the cost of the individual units down, and we can get them to be more or less autonomous, then we should be able to bring those costs down to really much, much, much lower than what it costs to do it with tractors, which is about $20 an acre, right? To maybe $5 or even less. Like by some estimates that we've done, it could cost as less as $1 an acre. But to do that, right, the thing that needs to get better is the autonomy. So what I'm calling here the MVP, or the minimum viable product, only makes sense at this level 3 autonomy, right, where one human is controlling many robots. Because so right now, if you go out there and try to plant cover crop on an 80-acre farm, it would take about 6 to 8 hours, right? So this is the one person, because they're using basically automated tractors, but those tractors are not at a level of autonomy where they can get out of the tractor. And I feel like while that's been a dream for a very long time, it's rather difficult because, it's just a lot of hardware moving around there, right? And even if you make it autonomous, I think it's the liabilities are quite worrisome with that. And of course, the issue with cover crops is that you can't even use those at the times you want to use them. So if you can get the robots, like teams of robots, to be autonomous, where one human is controlling many robots, and really eventually where that human is not even on the site, then these types of autonomy technologies really start to make sense. But the challenge, of course, once again, is not just to increase that level of autonomy, but bring the cost of that autonomy down. So we can't just make more and more autonomous robots by throwing lots of sensors on there. We got to get that cost down. So how do we do that? So in order to do that, we have to solve this kind of full path navigation problem, right? So the robot has to go turn around and come back out. And there's a quite complex architecture of control that needs to happen in order to do that. And I'm again not going to go through very much into the details in this particular talk, but there has to be a perception system that may use like a Bayesian filter, like an ECAF, a planner that may use things like multi-predictive control, and ideally an integrated planner and controller, and then eventually some kind of lower level motor controllers. Now, like I said before, most of the problems in robotics actually end up not just being the control, but actually the perception and sensing problem. So here the robot is following the rows, but then what it has to do is that it comes out of the row, it needs to switch to GPS because there really aren't any obstacle or any things now around the robot to use for the robot to navigate with. And then with GPS, then it has to make that end of the row maneuver and then get back into the row again. So these are challenging things and tasks, and lots of things can go wrong. For example, the robot heads can get caked up with mud. And if that happens, it ends up making mistakes, right? So first of all, it's hard for it to turn. Let me just forward it a little bit. But in this case, it goes in and it kind of makes a mistake and hits the corn. So a band-aid method that we have right now that we're publishing up on is this idea of like swapping through these different modes of control, detecting failures like this, and then automatically recovering from those failures. So with methods like this, we're able to get pretty good distance between interventions. But what we're not able to do is bring the cost down because we use the LiDAR. So in our more recent paper this year at RSS 2021, we have now introduced a vision-based row following system. So now instead of using the LiDAR, which costs $1,500, the robot uses a monocular camera to get the distance ratio to the row and an angle with the row. And this is work in collaboration with Saurabh Gupta and led by my student Arun. So in order to do that, we basically came up with this labeling system, the vanishing line labeling system, and a way to mark the horizon. And when the horizons are not visible, we mark the rows and along with some of these corn stalks, making the assumption that they're more or less straight. We correct for the viewpoint of this data with the robot IMU data so that we can correct for roll and pitch. And then we finally use that to train the neural network. And we've tried it out on pretty significant. This is just from the paper, was just 25 kilometers of validation. After that, this year, we've done many miles of validation. And it's very promising. I think vision-based autonomy is definitely the way to go. We've seen that it can deal with all kinds of weird conditions, like lots of occlusions, curving fields, that none of this data that you're seeing right now is a part of the training set. This is all validation. And now this year we validated entirely on a whole new year's worth of data. And we found mostly that it works. There are some domain shift issues that we're dealing with that are primarily coming from camera calibration issues and other things that always change on robots. But this idea of, I think, vision-based navigation is really promising, because not only can it enable good navigation, it also can bring the cost significantly down. And working with Vikram Adve, for example, we've been able to now reduce the size of these neural networks so that we can use much lower cost computers. So not Intel NUCs, but rather just use things like a Raspberry Pi 4 to get this done. And again, like it's, this is just another video showing some of the robustness of this system. So here, another thing that we've done this year, and my student Matthias worked on this, is this idea of controlling also the speed of the robot as a part of the MPC variable. So the robot is not just now controlling its angular rate, but it slows down when it thinks it's not able to kind of get, like get back on track by just maintaining constant velocity. So again, we're getting pretty good results now in terms of the distance between interventions. They're now getting into kilometers. So I think it's looking really promising. There are some major things that we have to deal with, and primarily they relate with row entry, robustifying row entry in all, like these types of condition, everything works great. But then there are like weird conditions where there's like a lot of corn either lodged or there's a lot of weeds in front of the robot. Then it has to kind of reason about what's the best way to enter the row. But the good news is that with this, we were now able to plant 100 acres of cover crop with this modified robot that we made using the same drivetrain, but completely re-engineered to carry 120 pounds of payload and spray seeds from under the canopy. So we did 102 acres this year, and it's all kind of coming up. So I want to definitely leave some time for questions. I'm going to try and finish in the next 5 minutes so that we can really talk about things. And maybe what I can do right now is maybe take some questions now. And then if we have time, then I'll cover some of the other things. But one of the, so let me just finish this and the next bit, and then we'll stop to take questions. So one of the other things that we've also been doing is working on the multi-robot coordination. And there's a number of papers that have appeared, including the most recent one in the Transactions of Robotics, in which we have created a new bandit-based framework for figuring out which row a weeding robot should visit, given that the seed bank density is not uniform on the field, and it's actually a hidden variable. Like you don't know what the seed bank density is until the weed actually emerges. So the team has to kind of solve this non-stationary bandit problem by figuring out which areas of the field are more susceptible to weed growth, and then minimize the number of robots by focusing the efforts on that. So the final thing I want to talk about is just getting back to this idea of polycultures. And I think the oasis gardens in the Middle Eastern history are, I feel, a great example that shows how water can be used when it is very scarce in a way to be really productive. And all of these polycultures kind of have this layered concept, right? So you have the bottom layer of vegetation, and there are some shrubs, and then there's a canopy that's kind of creating these pockets of sunlight versus not, so that you can really have different kinds of chemical processes going on. Now, the issue there, of course, is that the types of robots and human labor doesn't scale, but the types of robots we need in those environments also have to be dexterous and have to scale. So one of the things we've been working there is this idea of soft robot arms that can really be conformal to the different environments. And our RSS 2020 paper, we introduced with Girish Krishnan this hybrid soft robot arm and then control mechanisms for it. In that paper, we basically used reinforcement learning to reach berries, although the berry position was known to the robot in that paper. But now we have some new results that hopefully will come out soon about visually finding berries and reaching them. Okay, so I think I'm going to end here for this portion of the talk until we take some questions. But I think there's of course, a lot of applications of these robots in the desert. The Al-Baida project, which didn't use any robots, was very successful in reversing some desertification in some areas. So I feel like if there is a good investment made in these technologies, it's possible to kind of create robotic techniques that can create like basic ground covers on the desert and start reversing the process. So maybe let me stop, take some questions. We have 10 minutes, I think.
Thank you, Professor, for this exciting talk. This is really like, I see clearly many applications, many parts, like many topics. AI is inside, mechanical part is inside. So we have few questions, sorry. The first question is how to make the robots cost less.
Yeah, so I think at least the one I'm saying is that, so you have a different list of questions, I guess, but so how do you make them cost less is primarily by simplifying the amount of complicated parts that go in the robot, right? So things that cost the most in manufacturing are parts that are like gears, axles, differentials, drive systems. These are the things that cost the most because they're little parts. You have to make them very precise so that they fit just right. So by minimizing those is how you make the hardware of the robot cost less. And then it's not a robot if it is not autonomous. So you have to get the cost of autonomy down. But I made that disclaim that an electric robot should cost less than a tractor. And primarily that's based on this fact that diesel engines have just a lot of small moving parts. And to assemble all of that is really expensive. And the other way you can make things cost less is using scale, right? So if you make a lot of something, then the cost of everything comes down. And with what has happened with electric motors is there are so many other applications than just robotics that we can just tap into that market and find a motor that's used for something else and repurpose it for robotics. And that really helps us bring the cost down without having to make the scale of the robots become very large.
All right, I think Miftah take the answer. The next question is, aside from the many problems of farming, the lack of knowledge in soil and water management, pest and diseases detection still persists. Will it be possible to use or progress this technology to help our farmers?
Yeah, I mean, I'm sure. I think that's one of the major goals behind the Center for Digital Agriculture at EIUC, and many, I think, folks are trying to create techniques that can help farmers understand their crops better and then, take care of the land better.
I believe for this type of technology, also there should be a sensor system on the plants or in the soil that will give the answer, and then the autonomous robots that you have will collect the data and maybe will monitor in the farmer's screen. So the next question is, do you utilize a sensor for determining the ripeness of fruits and crops, or is it decided by humans? Also,
so the ripeness, I think it's a visual inspection. So if it can be done visually by humans, we think it should be possible to do it using cameras on robots.
And also, what is the effective range of integrated sensors?
So I think that a range of a sensor is really relative to the task it has to do, right? So for example, autonomous cars often end up being extremely expensive because they need to have very long range LiDAR sensors because they're trying to drive at 70 miles an hour. The robots don't have to drive that fast and they only have to see what's around them. So we are able to get by with sensors that have a range of about 20 meters.
Okay. The next question is there a work done where multiple integrated robot systems has been designed and collaborate in analyzing one field?
So yeah, I mean, that's the idea, using multiple robots to analyze and manage things on a field, like planting cover crops or getting rid of weed. So that's kind of exactly what we've been working on. This is what we like to call the scale neutral technology, right? So it's not just scales up like today's agriculture. It's only profitable at large scale, but also scales down so that small farms can use small robots. But the whole thing is because it's decentralized distributed system, you can just spread it across those different farms.
So do you have any study that like how many robots are required in a specific field?
Yeah. So in our studies, we've looked at cover crop planting. We think that 5 robots can cover an 80-acre field in about 6 hours if they're driving at 3 miles an hour, for example. And then weeding, it will take a little bit longer because the robots have to be slower. I mean, if you can make them faster, then it will reduce. So I think the 2 variables are increase the number of robots to bring the time down or increase the speed of robots. So that's really, how you can make sure that you can get things done in in the time that you want them to be done in a distributed system like this. Whereas on a tractor, the only variable you really have is the speed of the tractor, if you're using a single tractor. Yeah.
So, any other questions?
There was a question in my chat here about, don't the motors cost more? So I think the motors don't cost as much as a diesel engine, because just if you just look at the parts that are involved, right? Because diesel engines just have a lot more complex parts, and it has oil, you need to cool it down, you need to get the fuel, don't forget about fuel costs. So, and all the tubing, it's just really complicated to make diesel engines. Okay, then maybe I'll just end by putting forward some of these challenges that we think are good ones. So I think if you look ahead and if you're looking for topics to work on, I think one of the primary questions in mobile robotics is that of traversability, right? So how can the robot figure out how it can get from point A to point B without getting a very precise prescription of waypoints in the middle? Because it's not possible to provide that prescription every single time. The other one is edge cases. So finding obstacles, detecting, avoiding them, dealing with like all these weird types of obstacles that you might see is really challenging. Then getting robots to work across multiple fields and crops with different sensors is also very challenging. And this is kind of the classic domain shift AI problem. Plant manipulation is, of course, a classic problem in agricultural robotics. Then improving reliability of the whole system, bringing the cost down, improving fault tolerance is important. And then multi-agent coordination is also interesting, especially with lossy connections. Human-robot interaction, primarily also, I think natural language can play a big role as we try to bring this technology to farmers who are not, don't want to worry about having to program the robots using anything else than just like talking to them. And then making multiple robot systems work better across large scale using edge learning and federated learning, I think is also very important. And I just want to thank our Center for Digital Agriculture and our AI Farms National AI Institute and the UIC Autonomous Farm. And maybe I'll end by just showing this video of the FarmBot system that we now have there. And this is just a kind of more of an educational system where students have put this together, and we're using it to kind of simulate fully autonomous farming at a very small scale, of course. But these, I think the idea is that what we're learning here could be very useful in scaling this up to much larger farms. So if you have more questions, feel free to ask me, or you can send me an email.
We have one more question.
Yeah.
Do you plan on tackling vertical farms in the future with these ground robots?
Yeah, so I think vertical farming with robots is absolutely an area of interest overall. And I know that it is very important in the Mid East because of the lack of water makes a lot more sense to farm vertically. In the Midwest here in the US, it's not really that relevant because we have a lot of space. And I think if you do vertical farming, the robots would have to be very different than these ground robots. But that is absolutely the same technologies that we're working on would be very useful for vertical farming. Plant detection, planning, moving across different plants, approaching and manipulating plants.
We have one more question. So Elham is interested in reading about your work, Professor, where she can find the papers published. Is it accessible? I would say Google Scholar, your website.
Yeah.
When I make a small search on you on Google. I pretty find many information about this on your
Yeah, I
website.
think, yeah, Google Scholar is the best way to do it. I think you can find, if you just go to Google Scholar and look by year, mostly we try to either put an archive version out or publish in venues that are open paper, like RSS or those types. So you'll just be able to get the papers. And if you approach from university, I'm sure KAUST has access to those.